Obrigado. Boas tardes. I'm very sorry that I can't give the talk in Portuguese, but I wish I could. So let me share my screen. Hey, well, thank you very much for the invitation to speak in this session. I'm going to speak about joint work with Stéphane Truel, Georges Pereira, and Frédéric Touzé. So this is a project which has been completed completely during the pandemic. And we actually have a special thanks to Theorem because we were all supposed to meet there last spring. And they did an amazing job of somehow turning everything online to the point that at least we started talking to one another and doing some math. And we also owe special thanks to Pedro Freilich and Jon Marcout, whose work has played an essential role in what I'm going to tell you. And so we're really grateful for their having shared their work with us before it was made public. Okay, so this is a session on foliations, not about Poisson structures. So if you'll permit me, I'll just maybe give you a bit of a reminder of Poisson geometry, since it's maybe not standard for everyone. So a Poisson bracket on a manifold is a bilinear operation on the sheaf of functions, which has three properties. So first of all, it's skew symmetric. Second of all, it's a derivation in either argument. So here I've written it in the second argument, but it's the same in the first argument by skew symmetry. And finally, it satisfies the Jacobi identity. So, so points 1 and 3, they mean that this is a Lie bracket, and this Lie bracket is compatible with a multiplication by this derivation rule. So the standard example, which probably most people are familiar with, which comes from Hamiltonian mechanics. So you have a two-dimensional space with coordinates q and p, and you define this operation on functions, differentiation with respect to q and p in opposite orders, and that defines a Poisson bracket. This is a baby case of a Poisson bracket on any cotangent bundle. So if x is the cotangent bundle of some q, then I can choose coordinates on q, which induce coordinates on the cotangent bundle. And then the Poisson bracket is given by the same formula. Okay, it's independent of the coordinates. In a somewhat different vein, if I take a Lie algebra, say a finite dimensional Lie algebra, then there's a Poisson structure on the dual vector space, which has the property that if I take an element in the Lie algebra, I think of it as a linear function on G dual. So I say I take a basis for G, then the Poisson bracket of those coordinate functions on G dual is just their Lie bracket. So it's given by the structure constants of the Lie algebra. This determines all the other brackets by the Leibniz rule. And there are lots of examples coming from mathematical physics, so moduli spaces and so on. So for instance, if you take a compact surface, then the representations of its fundamental group into GLN, considered up to conjugacy, that's a, well, in general, singular variety, but it carries a Poisson structure. Okay, so many more examples. For today, eventually X is going to be a complex manifold, and I'll be dealing with a holomorphic Poisson bracket. So OX will be the holomorphic functions, but for the moment, I'm going to be a little bit agnostic about whether I'm working in the C infinity or holomorphic context. Okay. So one of the first thing one learns in Poisson geometry is that you can convert the bracket into a tensor. So the fact that it's skew symmetric and the derivation in both arguments, it means that you can write it in the following form. So the bracket of f and g must be given by pairing df and dg with a tensor pi, which is a skew-symmetric bivector. So the wedge 2 accounts for the skew symmetry, and the t accounts for the derivation. So in local coordinates, this bivector is looks like this, where pi ij's are some functions, which are the brackets of the coordinates. And then the bracket of any pair of functions now is represented in this form. So there's an expression which looks similar to that basic example, but now you take linear combinations of such things with pi ij coefficients. So that covers the skew symmetry and the derivation property. And then there's one more thing, which is the Jacobi identity, and that corresponds to a nonlinear partial differential equation, which is satisfied by pi, which says that the Schouten bracket of this bivector with itself is equal to 0. So the Schouten bracket is an operation on Pauli vectors, which generalizes the Lie bracket on vector fields. Okay, so continuing with the examples, these ones are going to be important for the general story. So a bivector is called non-degenerate if it defines a non-degenerate bilinear form on every cotangent space. So at every point, I can think of this element in wedge 2t as defining a bilinear pairing on the cotangent space, and I want that pairing to be non-degenerate. So if I have a non-degenerate bivector, then just by linear algebra, it means that the dimension has to be even, and the top exterior power of this bivector has to be non-vanishing. So then another way of saying that is that the bivector gives an isomorphism between the tangent and cotangent bundles. And so what I can do is invert the bivector and get a 2 form, which is also non-degenerate 2 form. Okay. And now the condition that this bivector is integrable, so it satisfies this equation, is equivalent to saying that the inverse 2 form is closed. So in other words, a non-degenerate Poisson structure is equivalent to the information of a symplectic form. Okay. And now one of the first things you learn in symplectic geometry is that there's a local normal form for symplectic structures. So near any point in the manifold, you have a symplectic structure, there's going to have to exist these nice canonical coordinates, Q and P, where the Poisson bracket takes on the very simple form like a cotangent bundle. And dually, the 2 form is just the sum of the dp's wedged to the dq's. This is the classical Darboux theorem. So in the 1980s, there was a very important paper which is often credited as kicking off Poisson geometry as a subject in its own right. It was a paper of Alan Weinstein. And one of the results in that paper is a generalization of the Darboux theorem to the case where we do not any longer assume that the bivector is non-degenerate. So here's what he proved. So let's suppose that we have a Poisson structure given by a bivector, and that its rank at some point in the manifold is equal to 2r. It always has to be even. So let's say it's 2r. Then in a neighborhood of this point, there are going to exist coordinates which come in groups. So there are q's and p's, like in the Darboux theorem, and then there are some z's. And the bivector looks like this. So the part of it involving q and p just looks like the bivector that we had for the Darboux formula. Okay. And then these z's are coordinates in the directions transverse to the p's and q's. And in those directions, you have some other bivector, which crucially the components depend only on z. So there are no p's and q's whatsoever in this thing I've called pi tilde. And moreover, this bivector, this red one, it vanishes at this chosen point x. So in other words, what we can say is that the Poisson structure has been split locally as a product of two pieces. So there's the green piece, which is a symplectic piece, and there's the red piece where the Poisson structure vanishes at a point. So it's a product of two types of Poisson structures. This red Poisson structure, the one which is in the direction transverse to the symplectic part, it has the property that it's uniquely determined up to isomorphism. So in other words, if I change the coordinates to some other system of Weinstein coordinates, I may get a different expression for this transverse structure, but that expression will nevertheless be isomorphic to the one that I've got. So this is the Weinstein splitting theorem. Every Poisson manifold is locally the product of a symplectic manifold and a Poisson manifold where the bivector vanishes at a point. Okay. Are there any questions so far? Okay. So one of the immediate consequences of Weinstein's splitting theorem is a decomposition of every Poisson manifold into symplectic leaves. So the way it goes is the following. If you have a function on a Poisson manifold, then it has a Hamiltonian vector field, which is the vector field corresponding to the derivation of bracketing with f. So you can define an equivalence relation. Say 2 points in the manifold are equivalent if they can be joined by a sequence of Hamiltonian flows for some choice of these functions f. Maybe you need a bunch of them to get from point to point. So these equivalence classes, they'll partition X into subspaces Lj. And from the Weinstein splitting theorem, you see right away that these Ljs are the leaves of a singular foliation. So they're immersed, in our case, analytic submanifolds. In the C infinity context, they'd be C infinity submanifolds. So each one of these submanifolds has tangent space given by the image of the bivector. So the bivector gives us a map where you contract a form into the bivector to get a vector, and that describes the tangent space of these submanifolds. So if you like, this is defining for you the tangent sheaf of this foliation. But one crucial thing is that because of the skew-symmetric linear algebra, if you have a subspace which is the image of the bivector, then it follows that if I restrict the bivector to this submanifold, then of course it's tangent to that submanifold, and it's not degenerate there. And so we can invert it along the submanifold to get a symplectic form on the submanifold. So every leaf of the foliation carries a symplectic form. So that's the picture of a Poisson manifold from a foliation theory point of view. It's a manifold which has a singular foliation, and all of the leaves are equipped with symplectic forms, and the symplectic forms, they somehow vary smoothly from leaf to leaf. Now, if the foliation is not regular, then you have to be a bit wary what you mean by the forms varying smoothly from leaf to leaf, and all you can really say is that they come from the bivector by this construction. Okay, so the extreme examples, when the bivector is 0, every point is its own symplectic leaf. And the symplectic form is 0, so that's rather uninteresting. the opposite extreme, we saw that you could have a pi being non-degenerate, and then the leaves of this foliation that I've just defined are, again, kind of boring. The leaves are just the connected components of x. So maybe that's not even worth considering as a foliation, but it counts in Poisson geometry. And then the form of the leaf is just the inverse of the bivector. Somehow in between these examples, we could have an example which is, say, constant in coordinates. So the bivector looks like this Darboux form, but there are some extra coordinates of z. So then the leaves are just the level set of the z coordinates. And the 2 form is given by this standard form restricted to every leaf. And so you get a kind of picture like this. You have a bunch of parallel leaves, which are all symplectic, but there are these additional directions that you can move. And by the way, it follows from Weinstein's splitting theorem that if the rank of the bivector is constant, then locally it must look exactly like this. There's no other flexibility. The transverse Poisson structure has to be 0. Okay, finally, we saw the case of a finite dimensional Lie algebra. The dual vector space is a Poisson manifold, and the leaves are exactly the coadjoint orbits of the Lie algebra, or the integrating Lie group. So this is a case where the leaves may have many different dimensions. Okay, one more example, because I'm going to use it on the next slide. So if I have a surface, then a bivector is the same thing as a section of the anticanonical bundle. So the 0 locus of the bivector is an anticanonical divisor, and I get 2 types of symplectic leaves. There's a 2-dimensional leaf, which is the complement of the 0 locus. That's where it's non-degenerate, and the 2 form is the inverse of the bivector. And then there are the points of this anticanonical divisor, which are their own symplectic leaf. So they're all a bunch of 0-dimensional symplectic leaves. So for instance, if x is P2, then an anticanonical divisor is a cubic curve. So it gets pictures like this. So the red curve is, each point on the red curve is its own symplectic leaf, and the blue part is a single open dense symplectic leaf. Okay. So again, maybe this looks like a bit of a funny foliation. It has an open dense leaf and then a bunch of points as the remaining leaves, but again, it counts as a foliation in Poisson geometry. Okay, so the problem that I want to discuss today is to what extent can Weinstein's splitting theorem, which is a local statement about the behavior of a Poisson structure, to what extent can it be globalized? So let's imagine that we have a Poisson manifold that is compact. Let's assume also that we have a symplectic leaf of this Poisson manifold. And the symplectic leaf is also compact. Okay? Now, in general, the symplectic leaves need not be compact. Of course, everyone knows lots of examples of foliations on compact manifolds whose leaves are not compact. But anyways, let's assume that we have a compact symplectic leaf. And then the question is it possible that our Poisson manifold X actually decomposes globally, not locally, globally, as a product of the symplectic leaf L and some other Poisson manifold? So this is playing the role of the green part in Weinstein's coordinates, and this is the red part, but it's now a global thing. So notice that if it decomposes in this way, then there must be some point in this transverse manifold Y where the Poisson bivector vanishes, because otherwise it would be impossible to find a symplectic leaf whose dimension was equal to the dimension of L. Okay. So I want a global splitting into a symplectic manifold and a Poisson structure whose vanishing locus is non-empty. Now, maybe it's a little bit too much to ask for a global splitting of X itself. So let's allow ourselves a little bit more freedom and allow ourselves to pass to a finite covering. Okay, so we can pass to a finite covering space of X and also of the leaf. Okay. So George was the one in our group who proposed that we investigate this problem. And my immediate reaction, I have to say, was like, there's no way that this is possible. I immediately started trying to come up with counterexamples, and it was easy. So if you work with C infinity manifolds, very easy to calculate, to construct counterexamples. So for instance, let's just take X. Let's assume that it's already a product of some L and some Y, where L is a symplectic manifold, a real symplectic manifold. Well, then I can define a bivector on X in the following way. I'll just take the symplectic structure on L, which defines this non-degenerate bivector pi L. And let me take an arbitrary smooth function on Y. Then I can multiply the bivector in the L direction by the function f of Y. What will this do? Well, it will mean that, for instance, the cohomology class of the symplectic form on each slice, each copy of L in the product, will vary depending on this function f. Okay? So the manifold is a product, but you see the Poisson structure is not a product in the sense that I've got above, because the bivector on the L direction depends on has coefficients which depend on the Y direction. Okay, so it's not decomposed truly as a product in the sense of Poisson manifolds. Okay, so there's an easy counterexample. But maybe that's a little bit artificial. So you may ask, well, can I find examples which are not themselves at least product manifolds? Maybe maybe the leaves are all isomorphic, but the manifold doesn't decompose as a product. Okay. So that's also easy to do, because there are many examples of these things called symplectic fiber bundles. So symplectic fiber bundle is what it sounds like. You have a manifold X, which fibers over some base. It's a fiber bundle over a base, and all of the fibers are symplectic manifolds, and the transition functions for the bundle are symplectic isomorphisms. It's very easy to construct these because, well, basically, whenever you have a bundle of Kähler manifolds, you can just take the fiber-wise Kähler form, and that will do the job. So, for instance, the simplest non-trivial example would be a two-sphere bundle over the two-sphere. There is a non-trivial such bundle. It's the smooth four manifold which underlies the odd Hirzebruch surface. So this gives a family of symplectic two spheres, which you think of as the symplectic leaves of a Poisson structure on this space X, so that the base S2 is like the leaf space of the foliation. So there's no chance that you're going to decompose this as a product, even though all the fibers are actually isomorphic as symplectic manifolds. Okay, well, what about in the holomorphic situation? Well, the first thing that came to mind was you could try to do the same thing and construct a fiber bundle, symplectic fiber bundle in the holomorphic category. You can do this, for instance, by taking a holomorphic symplectic K3 surface. There exist non-trivial bundles of K3 surfaces. Okay. Another thing that you can do is the following. So if you take, say, a compact torus, C to the 2n mod a lattice, then you can kind of form a twisted product with this torus and some other Poisson manifold. So here's why I was emphasizing the surfaces. Let me take, for example, P2 with the cubic curve given by a triangle. That's a the Poisson holomorphic Poisson surface, and I can act by the lattice on this surface just by basically toric automorphisms of this this toric surface. And so I can kind of form a suspension, if you like, a twisted product, where I take P2 cross C2 and I mod out the diagonal action of this lattice. And that will give me a fiber bundle over this compact torus, which has a section corresponding, 3 sections actually, one corresponding to each of these 3 vertices of the triangle. And those sections will define symplectic leaves in this Poisson manifold. So they're compact symplectic leaves. Okay. But there's a couple things to notice about these holomorphic counterexamples. The first one is that in the K3 case, the total space that you get is not a Kähler manifold. So if you, it turns out if you try to build a non-trivial holomorphic symplectic K3 bundle, it has to be non-Kähler. And in the second example, somehow the key feature that you're using is the fact that the fundamental group of this symplectic leaf L is actually infinite. Okay. So anyway, this is many counterexamples to the global splitting theorem, but what we realized is actually that these red points are the only obstructions in the holomorphic setting. So here's the main result. Let's suppose that we have the following. We have a compact Kähler manifold X. We have a holomorphic Poisson structure on this compact Kähler manifold. And it has a compact symplectic leaf. Okay. So maybe it's worth mentioning that compact holomorphic symplectic Kähler manifold is in fact a hyper-Kähler manifold. So these are very, very special objects. Okay, so here's the theorem, which we proved. The theorem says that given this data, if you assume that this compact symplectic leaf L has a finite fundamental group, then after passing to a finite étale cover, the Poisson manifold decomposes as a product of a symplectic thing, which is a covering of the symplectic leaf, and some other compact Kähler manifold with a Poisson structure that vanishes at least one point. So in other words, in the compact Kähler setting, if the fundamental group of the leaf is finite, then the global Weinstein splitting has a positive answer rather than a negative one, as in all those previous counterexamples. Any questions about the statement? So maybe let me point out a couple of corollaries of this theorem. The first one is that all of the simply connected compact leaves inside X pi are actually isomorphic to one another. So you could have imagined the possibility that there's one compact leaf sitting over here, another compact leaf sitting over here, and they don't know anything about one another. But actually, it's not possible. So kind of a strange thing. A second corollary is that there's a kind of failure of the idea of projective embedding in the context of Poisson varieties. So if you have a compact holomorphic symplectic manifold of positive dimension, then there cannot possibly be any way to embed this symplectic manifold into projective space as the symplectic leaf of a Poisson structure. The reason is that if you could, then by the theorem, you would split the projective space as a product of the symplectic thing and something else, which is not possible. And actually, I guess here I would need to say that L is has a finite fundamental group, but actually this corollary can be proved in another way, which doesn't require the finiteness of the fundamental group. Okay, so again, the theorem, you have a compact Kähler manifold with a compact leaf with finite fundamental group, then it splits after an étale cover. So let me make a couple more remarks about the statement. So first of all, if you know already that the manifold is split as such a product, then well, you can observe that the tangent bundle of X must split as a direct sum of the tangent bundle of the two factors. And moreover, this splitting is orthogonal with respect to the pairing given by pi. So pi is a pairing on the cotangent bundle, which of course is also split. So if the manifold does not have a split tangent bundle, then you're going to have a problem. But once you realize this, then you also see that the symplectic form on the symplectic leaf, it must extend to a global holomorphic 2 form on all of X, because I can just take the form on L and I can pull it back under the projection to get a 2 form on X. And actually, when you construct the 2 form in that way, what you realize is that the linear map, which defines the projection of the tangent of X onto the tangent of the leaf, is given by the composition of 2 things. So I have my global 2 form beta. I can contract a vector into the 2 form to get a covector. So it gets me from T to T star. And then I can contract a covector into the bivector to get a vector. So that gets me back to T. So this composition is an endomorphism of the tangent bundle whose image is TL. Okay. So these are basically like linear algebra observations about the statement. But the key thing is that rather than viewing them as consequences of the statement, we're going to try to prove them first. So the strategy is to first construct this kind of linear algebra data and then use it to split the manifold as a product. Okay. Okay. So let me explain how to construct these different pieces. So we have our compact Kähler manifold with a holomorphic Poisson structure and the compact symplectic leaf. On this slide, I don't need to worry about the finiteness of the fundamental group. It's irrelevant. So what I claim is that the holomorphic symplectic form on this compact symplectic leaf must extend to a holomorphic closed 2 form on all of X. Okay. And the proof is to use Hodge theory. So we have a compact Kähler manifold, has a Kähler class in H11. And let's let D be the dimension of this symplectic leaf, the complex dimension. Okay, and now I'm just going to take the Kähler class and the Poisson bivector, and I'm going to kind of chase around the Hodge diamond of X. Okay, so it starts like this. I have the Kähler form. I can take its dth power. I'll get something in HDD of X. Okay, remember D is the complex dimension of L. So now what I can do is take the bivector and contract with the top power of the bivector along L. So that's pi to the power D over 2. And that will knock down this omega D all the way to an OX. So it eats up the D form and spits out a function. So in that way, I can take this power of the Kähler form and I can produce a class in H0D. Okay. And now we know that this, by Hodge theory, is the complex conjugate of the holomorphic D forms on X. And finally, I can contract again with some power of the Poisson bivector to get me down to a 2 form on X. Okay, so this gives me a sequence of maps starting on the left and going to the right. So the line which is generated by omega to the d maps to some line in this vector space. Okay, so omega to the d maps to some holomorphic two-form beta. And what I claim is that this beta does the job. Okay, it's an extension of the holomorphic symplectic form on L. So to see that, we're just going to repeat the same sequence of maps, but we're going to do it on L instead of X. So I have L, I take its D forms. That's actually the top exterior power. So that's the canonical bundle of L. And well, L is a symplectic manifold, so the bivector actually gives an isomorphism from the canonical bundle of L to OL. So actually the first map is an isomorphism over L. The next one is complex conjugates isomorphism. And then finally, the contraction of a top form with a bivector, power of the bivector will always be injective. And so in this way, I see that this lower map is injective, and actually its image is exactly the line in this vector space, which is spanned by the symplectic form on L. Okay. And therefore, since this sequence is compatible with restriction to L, we deduce that chasing through this diagram that the restriction of beta to L is at least a scalar, non-zero scalar multiple of the symplectic form on L. So after correcting that scalar multiple, I get that beta is an extension of the symplectic form. So that's how you see that the two form extends. It always extends. This doesn't need the finiteness of the fundamental group. It just needs the compactness. But I claim something a little bit stronger is true. So not only does this two form extend to some closed two form on X, actually, we can arrange so that this composition I highlighted previously, beta composed with pi, is a projector. So it's an endomorphism of the tangent bundle, which is idempotent, so it squares to itself. And moreover, along the symplectic leaf, the image of this projector is the tangent bundle of L. So recently, Freilich and Marcoux, they gave a name to such a two form on a Poisson manifold. They call it a subcalibration. So I'm going to explain the proof of this proposition, but let me first explain why this notion of a subcalibration is important. So you see, because this operator is a projector, it means that splitting gives a splitting of the tangent bundle into the image and the kernel, which are complementary subbundles. And in fact, in the compact scalar setting, both of these subbundles are in fact integrable. So they define transverse foliations of the Poisson manifold. And moreover, the bivector decomposes in the correct way that we want according to this splitting of the tangent bundle. Okay. So this fact is a combination of some linear algebra of this projector and a little bit of Cartan calculus to check the involutivity of the foliations and so on. Okay. So it's a very nice notion which they uncovered. Okay, so how do we see that in the compact Kähler setting we can find such a subcalibration? I should say that they introduced this definition in the C infinity context, but the definition is the same in the holomorphic case. So how do we see that we can find this nice two form with this property? Well, we've already arranged a two form which is equal to the symplectic form when restricted to L. So this projector property, it already holds at least along the submanifold L. Okay. And so what that implies is that, well, the eigenvalues of a projector are always 0 and 1. The eigenspace with eigenvalue 0 is the kernel, of course. The eigenspace with eigenvalue 1 is the image. Okay. All right, but we have a compact complex manifold, and this P is a holomorphic endomorphism of the tangent bundle. And therefore, the coefficients of its characteristic polynomial are actually holomorphic, global holomorphic functions on X, which implies that the eigenvalues have to be constant. So in fact, the spectrum of this operator is always equal to the set 0 and 1 over all of X. And then if you look at the Jordan-Chevalier decomposition of such an operator, well, it must decompose as a sum of a projector and some nilpotent operator. And then some linear algebra will allow you to basically conjugate in a certain way to remove the nilpotent part. So you use the block decomposition, you kill off the nilpotent part, and in that way you arrive at the projector. Okay? And the only thing left to observe is that throughout this process, everything in sight remains holomorphic. And therefore, at the end of the day, you get a holomorphic 2-form on X, which has this projector property. And why is it closed? Well, it's closed because it's a holomorphic 2-form on a compact Kähler manifold. So Hodge theory assures us that it is closed. So that's the idea. You build the projector on the symplectic leaf, and then you extend it to some 2-form, and you correct it very slightly to remove this nilpotent part, and then you're good. Okay, so how does this help us? Well, if you have a compact Kähler manifold whose tangent bundle is split as a direct sum of integrable subbundles, then a conjecture of Beauville suggests that this compact Kähler manifold should decompose as a product after passing to the universal cover. It should decompose in such a way that these foliations that you have are exactly the foliations corresponding to the factors in the decomposition of the universal cover. So there are some known cases of this conjecture. Beauville already in this paper, he explained that it's true automatically if X admits a Kähler-Einstein metric. It's also known to hold when the tangent bundle can be written as a direct sum of line bundles. And so we can add now another case where this is known. So what we proved is that the conjecture holds in the situation that's relevant for us. So Beauville's conjecture holds if the tangent bundle is split as a sum of 2 complementary foliations with the property that one of them has a compact leaf with finite fundamental group. Okay. The tangent bundle splits into 2 foliations. One of them has a compact leaf with a finite fundamental group. Then the conjecture holds. And actually, a little bit more is true. So if the first Chern class of this leaf is 0, then you don't need to go all the way to the universal cover. Actually, just a finite cover will be enough. Okay. Okay. So so how is this case of the conjecture proven? Let's recall we have a involutive subbundle. Gives us a foliation into leaves. And we're going to use the holonomy of this foliation. So if we take a path in a leaf, then we get a holonomy transformation of every transverse slice to the foliation. So probably this is pretty standard for many people, but the picture is this blue thing is like a path in our leaf. And what we do is we push it off to a point in a nearby slice, and we follow point around a neighboring leaf, and it maps us to some point in a slice at some other point of the blue. So this gives a transformation from this slice to this slice, which is an isomorphism of the transverse germs of the foliations. And two paths are said to be holonomy equivalent if they induce the same holonomy transformation. Now, this is automatic if the paths are homotopic to one another inside this leaf. But in general, you could have two non-homotopic leaves which still have the same holonomy. And then, just like the fundamental group is the homotopy classes of loops, while the holonomy group is the holonomy classes of loops. Okay, so these can be composed in the usual way. And similarly, you can construct a special covering space of the leaf. So you choose a base point in the leaf, you consider all the paths which come out of it, modulo holonomy equivalence, and that will give a covering space of the leaf, which is called the holonomy cover. It's the covering on which all of the holonomy transformations become trivial. So for instance, if the leaves of the foliation are the fibers of a submersion, then all of the holonomy groups are trivial. And in fact, the converse is also true if the leaves are compact. Okay, so again, the leaves are fibers of submersion. This holds if all the leaves are compact with trivial holonomy. So how do you arrange all the leaves to be compact with trivial holonomy? Well, there's the famous Rabe stability theorem, which says that if you have a compact leaf of a foliation, which has a finite holonomy group, then all of the leaves nearby to L are also compact with finite holonomy. This is kind of a semi-local statement. It's a statement about a neighborhood of a leaf. But in the compact Kähler situation, Georges proved a very nice global version of this. So if you have a regular foliation on a compact Kähler manifold, and it has a leaf which is compact with finite holonomy, then in fact, every single leaf of this foliation is compact with finite holonomy. So it's a global Rabe stability result. So of course, in our situation, we have a compact leaf which has a finite fundamental group and therefore finite holonomy. And so this theorem applies. So when that happens, it means that the holonomy covers of all the different leaves, they assemble into submersion. At each point in X, I take the corresponding holonomy cover, and I assemble those into the fibers of the fibration over X. This is a fibration by compact Kähler manifolds, which has a name. It's called the holonomy groupoid. Okay. So now, how do we establish this case of the Beauville conjecture? So suppose that we have a compact connected Kähler manifold. The tangent bundle splits as a sum of two complementary foliations. And one of them has a leaf which is compact with finite holonomy group, so that actually all of the leaves of F are finite with compact with finite holonomy. Then what we do is the following. Okay, so first of all, we have two foliations which are transverse to one another. So it means that the leaves of G are giving transverse slices to the leaves of F. Okay. So now I consider what that means. I take the holonomy cover of all of the leaves of F. Okay. And then the leaves of G will still be somehow picking out the transverse directions. And so what they do is they give me a flat connection on this fiber bundle. Okay, so the holonomy covers they assemble into a fiber bundle, which has a flat connection in the sense of Arrowsman, which is induced by this complementary foliation G. So that immediately tells you that all of the holonomy covers are isomorphic to one another, because if I have a flat connection on a fiber bundle, then I can take the parallel transport along a path, and that will give me an isomorphism from one fiber to another. Okay, but it tells us more, in fact. So the holonomy group, it comes from considering paths in the fixed leaf L and how they act on the transverse slices of the foliation. But now we can observe that since this bundle has a flat connection, actually the fibers carry an action of the fundamental group of X. So pi1 of X acts on the holonomy covers, and this is an extension of the holonomy transformations along the leaf. So now each one of these holonomy covers is a compact Kähler manifold, and we know quite a lot about the automorphisms of compact Kähler manifolds thanks to work of Lieberman. So using his structure theory for the automorphism group, we were able to check that there necessarily exists a finite index subgroup of pi1 of X, which has the property that it intersects all holonomy groups trivially. All holonomy groups trivially. And what that means is that if you pass to the covering space of X, which corresponds to this subgroup gamma, then you'll obtain a situation where, well, of course, passing to the covering space, you can just lift everything to the covering space. You get transverse foliations on the covering space. But now, on that covering space, the foliation F has had its holonomy trivialized. So it must be the fibers of a fiber bundle. And in this way, you arrange to split X tilde, split the covering of X as a product of a covering of the leaf and some transverse Y. Okay. So that gives the proof of the Beauville conjecture in this case. As for this bit about the case where L has a first Chern class equal to 0, well, that follows from a little bit more refined information that we have about the automorphism group in the case of Calabi-Yau manifolds. Okay, so it's almost time to finish. Let me conclude by putting it all together to prove the global splitting theorem. So let's suppose that we're given a compact Kähler manifold, a holomorphic Poisson structure on this compact Kähler manifold, and a compact symplectic leaf whose fundamental group is finite. What I want to do is show that after passing to an étal cover, the thing splits as a product of Poisson manifolds. So what have we shown? Well, we started by showing that the 2 form on the symplectic leaf can be extended to a subcalibration in the sense of Fröhlich and Marcuse. Okay. So remember, that's used the Hodge decomposition of X. And then we said, well, once you have a subcalibration, it gives a splitting by splitting the tangent bundle into 2 complementary foliations such that the leaf L that we're after is a leaf of F. Okay. So this is just a Fröhlich-Marcuse result. It's true for any subcalibration like this. And then, we now have a regular foliation F, which has a compact leaf with finite holonomy. And so by the case of the Beauville conjecture, which we verified, it follows that the manifold now splits as a product. after this finite étale cover. Now, there's just one thing missing, which is, I emphasized earlier on that telling you that the manifold itself is a product is not quite what we wanted. I wanted it to be a product of Poisson manifolds, so I need to show that the bivector on x tilde is really coming from the bivector on L tilde plus the bivector on y. Okay, but this is actually immediate because if I look at the bivectors on x tilde, well, this is a holomorphic vector bundle, and so I have a Kunneth decomposition for the global sections. It decomposes as a direct sum of the bivectors on L tilde, the bivectors on y, and the cross terms where I have like a tangent direction along L tilde and a tangent direction along y. But in this subcalibration, remember I emphasized this key point that the Poisson bivector is orthogonal with respect to f and g. So the Poisson bivector has no component, which is a cross term. That was already true at the level of this splitting of the tangent bundle. So what we conclude is that there's no possible cross term here, and the bivector must be the sum of its projection on the two factors. And that's the proof of the theorem. So thank you very much for your attention, and thanks again for the invitation to this nice session.